started. Oh, all right. Can everybody hear me? I'll just assume that everything's all right and I'll start sharing the screen. All right. Can everybody hear me? Looks like I might be frozen. I can't really tell. Can somebody unmute and say something? I want to test my connection. Okay, sorry about that. So it looks like my Wi-Fi is really bad right now, but I'll just try to continue anyway.
Oh.
All right, so welcome back to the next class. This is like the 13th class in the summer and winter combined. Oh yeah, if I seem to freeze or anything, please shout out so that if I'm not frozen, I can answer you. If they don't say anything, then you can assume that something's happened to my internet. All right, anyways, let's jump right into it. So today we have combinatorics review. And well, actually, we decided to assign the AMC practice test next week, not this week. So yeah, this week's homework will be number theory is what we're covering. So cross this out. Okay, anyways. So let's jump right into the homework. So first, Jeremy has an unfair coin that lands tails twice as often as heads. What's the probability he flips more tails than heads in 3 flips of this coin? I'm just gonna go over all of these myself. Well, if he flips tails twice as often as heads, both the two outcomes are heads and tails. They sum to 1. So that means tails is a probability 2/3. Head is 1/3. Pretty straightforward. If he flips more tails than heads, he can flip 2 tails and 1 head, or he can just flip 3 heads. So we calculate the probability for each of these cases. We can arrange TTH in 3 ways, so you need to account for that. And then 2/3 squared, sorry, for the 2 t's, and then times 1/3 for the h. This is 12 or 27. Meanwhile, this is just plain, or not HHH, sorry, this should be TTT, right? This is just a plain 2/3 cubed, or 8 over 27 for this total of 20 over 27. All right, now I think this should be pretty clear. It's just like casework, except with probability. Really, it's just counting, but like an extra step. Okay, 3 of the vertices of a rectangular heptagon, 7-sided polygon, are connected to form a triangle. What's the probability that 2 of the triangle's sides have the same length? Okay, so let's see. First, it'll be useful to draw a relatively regular looking heptagon, right? Like this. For these kind of polygon problems, I would find it useful because like a lot of these diagonals, like this and this, you can just like intuitively tell because it's a regular polygon, they're going to be equal. So I would just label all the possible different chord lengths. Like I'll call this, I don't know, 1. This, well, this will be 3. Sorry, I jumped it. And this is 2, since like this one, the minor arc has 2 points, this one has 3 points, and this one is just 1 point. So anyways, now that we've defined like our possible different arcs, we can just look for the different triangles we can make. You should always like start out by trying from small to big in these. There are actually not many cases. So the first one is when you have this triangle here, which has 2 of the heptagon's length and this like small diagonal. That's like a 1, 1, 2. The second case if we have that, this is the smallest side, and then we have another 2 here, and then this is a 3, so it's like 2, 2, 3. And for those of you who are intuitive about geometry, we can tell we're not going to run into the problem of counting anything that's equilateral and to have to account for that. So since it's a heptagon, so we're good. Lastly, we can have one that's like this, which is these are 3s, and then this is a 1. And so yeah, that would be 3, 3, 1. You can just kind of do casework on like what the equal side length is, and you can reason these are actually the only 3 cases. Okay, so now how many of each of these cases are there? Well, for each of these types of isosceles triangles, we can just pick one like vertex of the heptagon to be the vertex opposite the base, meaning that these 2 equal legs jut out of it. So there are actually just 7 of each of these, right? Because any of these can be the vertex. In that case, we would have 3 times 7 total. And how many total triangles we can have? Well, a triangle is just defined by any set of 3 points, not order specific. That's just 7 choose 3. If we calculate this, that's 7 times 6 times 5 over 6. That's 35. 21 over 35 would be equal to 3/5, hence our answer right here. Is that clear to everybody? Okay, that should have been, these shouldn't be too hard. Just make sure you get your distinguishability right, and do your casework like judiciously. Okay. One remark is that like this 1, 2, 3 thing may not seem that useful because it's like a heptagon and pretty simple. But trust me, if you have like, I don't know, an 11-sided polygon or something like that, it could probably like save you like a lot of hassle. Next is the digits 1 through 9 are divided into 3 sets of digits, 3 digits. What's the probability that the product of one of the sets is odd? Okay, now right off the bat, there are 5 odd numbers among this set: 1, 3, 5, 7, 9. So we can only have at most one set of 3 odd numbers, which is what we must have to guarantee that the product is odd. All right. So remembering our like cautious warning of the ordering of choosing sets from last time, the amount of ways total to choose sets, not, of course, we don't count the order in which we choose them to make them distinct. 9 choose 3 times 6 choose 3 over 3 factorial, right? Okay. Now on to the numerator, which is the number of ways to choose the sets such that one has an odd product. 5 odd numbers, choose 3 from them. And then we just multiply by 6 choose 3 times, there's an implicit times 3 choose 3 in this as well, over 2 factorial, because this is just like the same thing except with 6 numbers and 2 sets. We don't really care about what happens because we know we can't get another odd set. All right. So if we divide this by that, we cancel this 6 choose 3. These are just 1, they're irrelevant. This and that cancel to bring a 3 up in the numerator. 5 choose 3 can calculate is 10, so far it's 30 over 9 choose 3, which is 30 over 84, which divide by 6 top and bottom gives you that. My work was a bit all over the place, but I hope it wasn't too hard to follow. You can always shout out if you have any questions. Okay, so now you choose 3 dates in history at random. So what's the probability that at least 2 of them occur on the same day of the week? Notice we have our like key pointer word here, at least. So that's a signal for complementary counting. It also could signal principle of inclusion exclusion in some problems, but I feel like that could be a bit advanced for the AMC 8, but keep that in the back of your mind too. Or possibly could involve both complementary and principle of inclusion exclusion. But anyways, so for each of the days, there's 7 possibilities, right? Could be any 7 days of the week, 7 cubed. Note that if we have like one Monday, Wednesday, Thursday as our days of the week, we can swap them around and this will count each of those as distinct. So we must count the numerator so that it's consistent with the denominator. So how many ways are there to choose 3 different like occurring days? Well, that's just 7 times 6 times 5 if we want to match the ordering. Cancel this 7 here, that's 49, 30 over 49. Don't forget, subtract it from 1, gives you this, 19 over 49. A note about this, if you wanted to make this like 7 choose 3 and count this kind of unordered, you have to do some like, you could do it, but you have to do some casework. So I would just recommend doing it like this way in which you count order. Okay, now, so that's all the homework problems. If you don't have any questions, I'll move on. And again, shout out if I seem to freeze or disconnect. Okay, so let's move on to number theory or today's topic. For number theory, it's often really useful to find the prime factorization of a number, the unique way not including order. Number theory is very centered around primes. So it's very useful to consider what primes divide a number, how many of them do. And so first check if a number is itself prime. You only need to test to see if it's divisible by prime numbers actually up to its square root, and we'll see why that is later. In addition, we only need to do that because like factors kind of pair up. Like there's, let's say you have number like 40. Well, 1 and 40 kind of pair to multiply to 40, 2 and 20 do too. And you can see that like if you only like check up to the square root, you're good, because if this doesn't have any factors on less than equal to the square root, then there can't be a corresponding factor in here greater than or equal to that'll multiply it to this. All right. Okay, now that was just a short note on why that works. So examples are 181 and 287 prime. If not, what are their prime factors? Okay, you can just like shout it out. This should, or like, just take a time to just check, but you can just shout it out whether or not. All right, so I see someone said 181 is prime. That's right. Just to go through the process of it, what are the primes less than the square root of 181? That's up to 13. Somebody said 287 is composite. That's also correct. So 181, the primes are 2, 3, 5, 7, 11, 13. These you can eliminate very easily if you know divisibility rules. Same with this, actually. So you just need to divide this by 7 and 13. This gives a remainder of 6, and this gives a remainder of 12, so it's prime. 287, some of you, I guess the thing that jumps out is it's just like a 28 next to a 7. So you can just divide by 7, you get 41. And it's just 7 times 41. Anyways. Okay, so now we will move on to number theory and the fundamental theorem of arithmetic. Oh yeah, by the way, since the TAs are all now here, you can private message them too, and I will change their names to reflect that. And yeah, now we will just jump into more number theory stuff. So the fundamental theorem of arithmetic is another fundamental theorem just like that of counting. And this time it states that every number has a unique prime factorization, has exactly one, okay? For example, 5544 is 2 cubed times 3 squared times 7 times 11. This means that like, these are like exponents, of course. Like how many 2's divide this number? 3 of them. And 2 3's divide the number. There's no other way to factorize into primes than this. To find this, one basic strategy is to make a factor tree. Whenever you find a factor of the number, split the tree into 2 branches, split the factor. Like, let's say you found 12 as a factor here. Well, one branch goes to 12, the other factor goes to this number, the top 120 divided by 12, which is 10. And then you just like recursively factor tree those. Eventually, you stop when you get to the prime numbers, and in which case you'll always end up with all of the primes. So let's see, there's 3 2's, 1 3, and 1 5. 8 times 15, 120. Perfect. Given that, and you can just, I'll have you like do the prime factorizations of these two numbers, 440 and 432. All right. It should be like pretty fast, so I'll just give you maybe 1 2 minutes. Oh yeah, use the caret symbol for exponents and the asterisk, which is shift 8 for multiplication, please. Which we will be using as pretty standard. You could also use x just for this week, since it's not confusing anything. All right, so I see someone already got 440. This is just 44 times 10, like that's what jumps out to me. That would be 2 cubed times 5 times 11, since this is 2 squared times 11. This is 2 times 5. Combine them, get this. All right, no, not too bad. Okay. So I see somebody else also got 432. We'll just go over that. This one you might need to divide more. I don't know. The first thing that jumps out at me is just 4 times 108. But that's, I don't know. You can think about it any order you want. And this is 2 squared. I just happen to know this off the top of my head is 4 times 27. So the right answer is 2 to the 4 times 3 cubed, which is what you all are getting. So that's pretty good. It looks like you guys are pretty like well-rounded in the basics. So yeah, let's move on. So perfect squares. Well, we have this prime factorization here, right? How can we tell whether a number is a perfect square from it? Well, each of the prime factors must have an even exponent in its prime factorization. If we cut each exponent in half, we get the square root. For example, is 3 squared times 5 to the 4 times 7 a perfect square? And what's the square root of on this number? 2 squared times 3 to the 6 times 5 squared. What about this? 2 to the 4 times 3 squared. Because if it is a perfect square, we just take half of each exponent, then we get its square root. If it's not, then we'll try to like have something that we can't and get like irrational numbers. So yeah, I see somebody just said, no, this is not a perfect square. That's right. There's this like 7 to the 1 causing some trouble. So yeah. And you all are fast, so this is just 2 times 3 cubed times 5, as you said, just like half each of these 2, 6, 2, 2 to the 4 times 3 squared, 2 squared times 3. All right, not too bad. And as some of you said, this is 10 times 27, 270. This is just 12. Yeah. Perfect squares. Note that like you want to what you want to do is you want to understand like how these conditions, like whether numbers are perfect square, the exponents are multiple of 2, perfect cube, the exponents are multiple of 3. You want to really like understand how that reflects in the prime factorization of the number. Like if you have a very good understanding of the prime factorization, what each exponent means and can tell you about the number and what they can tell you together, then you'll be able to actually get very far. And now we will move on to like one of the most pervasive things, which is counting the number of factors a number had given its prime factorization. We can just list them. Like this thing right here says for 40 that you can go like 1, 2, 4, 5, and then now we're past the square root. So we can just pair up 8, 10, 20, 40. This is like the line where the numbers are less than or equal to the square root and the rest are greater. Keeping them in track of pairs like this is very useful if you don't want to make mistakes here, but for large numbers, this is still very error prone. Although I will say that if you like conceptually think of factors as being able to form these pairs, that can also help you to derive some useful results later on. But now is not the time for that. There's an easier way to do this using prime factorization. Consider 40 is 2 cubed times 5, as it says right here. Every factor of 40 can be written as a product of 2s or 5s, possibly 0 of these prime factors, right? Because like 5 divides 40, but how many 2s does 5 have in it? None. And if there's 0 of each, it's just 1, which just trivially divides all numbers. And if we're creating a factor, the exponent of 2s can be 0, 1, 2, or 3. Note that this is one more, that the amount of choices is one more than the exponent itself because there's that extra 0 we have to account for. And then the exponent of 5 can be 0 or 1, okay? Since it's 1 more than 5 to the 1. And of course, I think you all know this, but like if there isn't an exponent written here, it just means the 1, the first power. So anyways, creating a power, we have 4 choices for the exponent of 2, 2 for the exponent of 5, and so that gives us 8 factors. Lo and behold, there are 8 factors in total over here. All right, so checks out. In general, we look at the exponents and prime factorizations, add 1 to each and multiply. Make sure you know why, because this is essentially like if the exponent of a prime is n, we want to see how many numbers 0 all the way to n. That's n plus 1. So you multiply like all of these n plus 1s for the different primes together. It's just really a counting problem and counting like things in succession that are independent of each other. Now, how many factors does 56 have, and how about 240? Oh yeah, and please like try to private message the answers if you want to like, so everybody has a chance to do them. Oh yeah, note that we want to like count how many factors it has. Okay. Okay, just I'll give you a second to work out 240 as well.
Will it tell us if we're correct or not?
For these problems, since they're pretty, for the later on, there's some harder problems which I'll individually and TAs will individually tell you. But for now, I think it's simple enough, so you can just shout it out, and if I say the same thing that you did, you got it right. All right. All right. So how many factors does 56 have? Well, 56 actually follows the same structure as 40. It's 2 cubed times 7. Okay, sorry, somebody is like making noises. Okay, anyways, so that would just be 3 plus 1 times 1 plus 1 is equal to 8. And for 240, we have already factored it for you. Okay, so that's just 5 times 2 times 2. Okay, 40. And in that case, we can just move on, given if you know how to do this. Make sure you read like correctly what it's asking. If they say not to include the number itself or 1 as the answer, be aware of that. All right. So moving on to more problems, we also have restrained factor counting. Sometimes they will not ask for all the factors, but instead, even factors, odd factors, or perfect squares. Again, you really need to be conceptually solid in what every single number in that prime factorizations means. And if you are, you will really easily understand how to get each of these quantities. To do this, remember the basic concept why factor counting works, because you can choose any exponent for any prime. And for odd factors, what does that mean? 2 is the prime you care about here. There can't be any 2's in it. And it's the opposite for even numbers. There must be a 2 in it. So let's say you had a number like, let's just take this, okay? 2 to the 4th times 3 times 5, okay? If we're taking about odd factors must divide this part, 3 times 5, in which there's case 1 plus 1 squared is equal to 4 factors. And if it's even factors, we can just exclude these and take total, like this total is 20 minus 4 is 16. You can do it like that, or you can say, oh, the exponent of 2 must be positive, so it goes from 1 to 4. So it'd be 4 times 2 times 2 to 16. Really, either way works, as long as you know like why this works, what we're doing. Perfect square factors, well, as we said, the exponents in perfect squares must be even. So we just count out instead of how many total choices, how many even choices we have. Let's just take a different example. 2 cubed times 5 to the 5th. What can this exponent be to make it a perfect square? 0 or 2? What can this be? 0, 2, or 4? So our answer should be 2 times 3 is equal to 6. All right. I hope that makes sense to everybody. Why like this works to count all these factors. Okay. Another example here they gave. 1440 is 2 to the 5th times 3 squared or 1. Our options are for the exponent of 2, we have 0, 2, or 4, and then 3 can have 0 or 2. 5 can only be 0, so there are 6 square factors. We can verify this by listing them out since, yeah, I mean, like if you really want to and have time to during the test, you can, but like you might not have time, so yeah. Okay, so restrained factor counting practice and things to recall. Remember to consider the possibilities for each exponent. For the odd For odd, the exponent of 2 is 0. For even, the exponent 2 is at least 1. And for squares, all exponents are even. And really, you should be able to easily generalize this to other numbers too. Like, let's say you wanted the factors of a number that were divisible by 3. Well, then it would just do the same thing. But if it's divisible by 3, the exponent of 3 has one less choice than for all the factors of the number in general. And if it's not divisible by 3, the exponent of 3 must be 0. All right. I hope that's good with all of you. And same thing with like perfect squares. All exponents are even. For perfect cubes, they're all multiples of 3, etc. There are also other important things regarding number of factors. Note that since all the exponents in a perfect square are odd, but the exponents in a perfect square are all even, it will have an odd number of factors because you're adding 1 to all of these even numbers, then multiplying them after that. That's just a product of a bunch of odd numbers. All right. And you could see that otherwise there will be some exponent that's odd, not making it perfect square, that'll make the answer even. And here are some practice problems. Oh, and I would like to mention, when you are doing casework in these problems, like let's say you want to find like number of numbers of the form PQR where these are distinct primes and this number is less than or equal to 120 or something. You should do cases on like what the smallest prime kind of is. Like let's say 2 is our first case, right? And then we want to find numbers that have this form are the product of 2 primes. Note that we want to do casework such that we don't accidentally we don't want to accidentally do q's too, because then that wouldn't be if the form would be 2 squared. So just be wary of that when you do the other problems, because I know this is a mistake I often made, like counting something that had prime overlap is what I call it. So just like be aware of prime overlap, don't do it, and like organize your casework carefully so that this won't happen. All right, anyways, we have some harder problems and examples to go over. So how many factors of 1296 are perfect squares, and how many factors of 440 are even, how many are odd? How about the factors of 480? And another example, a number n has exactly 7 factors. How many factors does n squared have? All right, now I'll let you loose on these problems, and I'll give you a little bit to do it. Oh yeah, make sure you read the problem correctly and see what it's asking exactly. Oh yeah, and for number 1, please state, like, if you don't do all of them, just please state which number you're like submitting for. And yeah, be careful when reading.
To rock the night away.
Dog.
Please don't shout out things unrelated to class. Oh yeah, please. If you have an answer, you should just like summon it. All right. Okay, let me just go over number one. Seems like a decent amount of people have gotten certain parts of it. Let's tackle 1296 first. I realize this would probably like daunt you guys a little, but I just happen to know that this is 6 to the 4th power, and this has a prime factorization of 2 to the 4th times 3 to the 4th. Well, how many choices does that give us? This we have 0, 2, 4 for perfect square. This we also have 0, 2, 4. Just 3 squared is equal to 9. You can list them out if you want to confirm. How many factors of 440 are even? Well, we know 440's factorization from earlier. If it's even, this exponent can go from 1 to 3. If it's odd, it must be 0. So even would be 3 times, let's see, 1 plus 1 squared for these two. And then odd would just be this, giving 12 even, 4 odd, for a total of 16, which checks out since it would be 3 plus 1, 1 plus 1 squared. Okay, so yeah, 16 total factors. 12 even, 4 odd. How about the even factors of 480? 480 should be 2 to the 5th times 3 times 5, or 10 times 48. This has 4 choices. These two both have 2 choices, given that it has to be even, so 4 times 2 squared. It's equal to 16 in total. All right, now quickly to go through this. This problem, I would say it's kind of like a nested number theory problem, because first you have to see how many ways you can split 7 into a product of different numbers based on factor counting that arise from factor counting. You first have to see like how you can factor 7. All right. So yeah, take a crack at this, and it's really not that simple if you don't overthink it. So yeah, it's really not that tough if you like think about it right.
7 is prime, so it has to be.
Yeah, don't call out the answer though, unless like you want to give a solution. Actually, I will give you opportunity to present like solutions you want now. After this. All right. So somebody got it. Okay, so Steven, you were going to say earlier, you can unmute and explain now if you wish. Yeah, you can just unmute and go ahead.
Okay, so because the number n has 7 factors, it can basically only be factored into 1 and 7. So it sort of means because 1 minus 1 equals 0, and 7 minus 1 equals 6. Yeah, 7 minus 1 equals 6. I'm just going to say P1 is a prime. P1 to the 6 is the number. So when we screen this number, it becomes P1 to the 12th. And P1 to the 12th, when we put it back in, P1 to the 12th gives us 12 plus 1 equals 13.
Exactly. Now, for these kind of problems, first you want to figure out how this number factors. And these will be the products of like the factor counting counts for the exponents of each of the individual primes, if you know what I mean. And as he said, conveniently 7 is prime. So we only want factors that aren't equal to 1, because like if it's equal to 1, that means it's to the 0th power, which doesn't really help. So then it's just a prime to the 6th power square. We get a prime to the 12th power, and easy, that's just 13, given our factor counting methods. So yeah, that's how you do this problem. Really not that hard if you get it and everything. So yeah. Now we have more problems. So again, like specify what number you are answering. For those saying about the Zoom meeting ending, I think mine actually shouldn't end, but if it does,